Good morning, everybody. This is the webinar, How to Implement an ISA 84 Compliant Safety System. If you want to join the teleconference by audio and suppose you don't hear anything, then you call these numbers and enter your access code. The webinar will start now. This webinar will take about 45 minutes, after which we have a Q&A session for about 10 to 15 minutes. Due to the large numbers of participants, every participant is muted. Questions will be taken through our QA window, which you will find in the menus that the WebEx is providing you. Please send questions to all panelists so everybody can read what you're asking. Questions will be answered at the end of the presentation or after the event by email if necessary. Shortly after the event, you will receive a link with the recording of the event, and your feedback is very important to us, so please complete the survey at the end of the presentation. My name is Jan de Briet. I'm a technical solutions consultant with Yokogawa Corporation of America. We are based in Sugar Land. I've been working since 1988 in the safety systems industry in research and development, field service, operations, sales, and marketing. So, here's the introduction to this presentation. You will get answers to a couple of questions and some more knowledge. First, why would one replace a safety system? Why would one be compliant with the ISA 84 standards? What is the ISA 84? I will give you an overview of this standard. And what would you need to do to comply with this standard? And why would you choose Yokogawa to help you in that process? So why would you replace a safety system? Well, the current situation in the safety system area in the plant and process industry is that we have a very large installed base of aging safety systems. These systems need to be replaced. We have, for instance, old relay and pneumatic that need to be replaced. We have old technologies, so those technologies are not compatible with current network and other communication options and Windows softwares. And people that know about these systems are also getting older, and they will disappear from the labor field by retirement. And many products that are getting old are facing an end of product life, so there's no more support for those systems. Even if you have a very high reliable system, that could mean that you have used that system for very long already, and then the equipment gets older and older and is bound to have more failures over time. And sometimes by acquisition through other parent companies, there could be a variety of different systems in your plant. And for each of those, you need specialized knowledge, and that is quite an organization to maintain. This may all lead you to decide that you need a new safety system. So, why would you choose ISA 84 compliance? Well, major incidents, recent as the Gulf oil spill, will ask for better safety because of liability and insurance premiums, which are going to be in astronomical figures if the safety is not well regulated. And even if you have a good personal safety management, plants are still at risk from process hazards. A control system can break down, and that could lead to a very dangerous situation. So, and OSHA requires that you shall perform good and use good safety standards. That is process safety management. OSHA says you shall use good engineering practice for your safety system. And one of the good practices is, of course, the ISA 84, and the ISA 84 has what we call a grandfather clause. Grandfather clause is a clause that has been used quite widely up till now, and it basically says that you can use whatever you have, and at least that is the common opinion of this, but that's not so. I will do that first. I will show you why you can't use a grandfather clause. This is what it literally says, that for an existing safety system, you can still use that if it is prior to the issue of this standard. But you also need to design, maintain, and inspect, and test, and operate this system in a safe manner. That last one is a very devious one. Note at first, the issue that is related to in this clause is 2004. So if your system is from 2004, you will have to comply with ISA 84 if you want to replace it. Note also that the first issue of this standard that had this clause is from 1996. So also systems that are from then. The only way you can grandfather your safety system right now is through if you do very basic upgrades, like repairs, replacement in kind. If you change the technology, even if you think it's better than what you have, you cannot use the grandfather clause. So the grandfather clause is very hard to keep up to date. If you have a system from before 2004, of course today it's 10, 11 years old, then the equipment gets older and older. You may not be able to buy it anymore, and the system may run already out of its useful life. The other thing, of course, is the grandfather clause is a highly discussed topic. I could spend a whole webinar on discussing this topic, but in the end, in quotes, de facto, it's not possible anymore to use a grandfather clause to use as for your safety system. So we are looking at ISA 84. This is the most widely used standard in the industry, and ISA 84 is completely the same as the standard used in the rest of the world, IEC 61511, and that is how globally safety systems are done. So I'll give you an overview of the ISA 84. The official title is ANSI ISA 84 0001 2004. Functional safety instrumented systems for the process industry sector. It has three parts. The first part is the standard, and that describes the safety life cycle and all the requirements that apply. And the other two parts are mainly the guidelines and examples for how to achieve the required safety. The main characteristics of this standard is the management of functional safety, the safety life cycle, the pipe-to-pipe approach, and a quantitative safety assessment. I will go through these four before I start with the life cycle. The management of functional safety. So you must have a functional safety management system in place. That's what the standard says. And this management system must specify all the management and technical activities that are necessary to achieve the required functional safety. So you have to specify the life cycle of your safety systems. And life cycle is, of course, from design till decommissioning. We will see that later more and more in detail. Then you have to have procedures, how to make sure that everybody follows these standards. Then different responsibilities in your plant need to have certain competencies. You have to prove that. Then you have to have procedures in place that will describe how to verify certain verification actions, such as the approval of documents, and that will show how you validate your system to say it's safe. And this management program needs to be auditable and traceable. Any change to your safety system must be traced from the initiation to the final outcome, how this change has been implemented. The safety life cycle is shown here. On the left-hand bar, you will see the management of functional safety. That is what I just talked about. Then the safety life cycle, you can describe that for yourself, but the main routines, the main procedures are in the middle. And in the end, everything that is produced in this safety life cycle needs to be verified. That is the verifications, and all of that needs to be documented. So next to the functional safety management, the IEC or the ISA standards asks for a pipe-to-pipe approach. Safety is regarded from pipe to pipe, so it includes the transmitter and it includes the valve. And in the middle, we have a logic solver that will perform the safety functions. Next to that is a quantitative assessment. The safety functions are called SIF, Safety Instrumented Function. The safety instrumented function will give you risk reduction. It will reduce the risk of a certain hazard, and this hazard, of course, has been done in the HAZOP. I'll tell more about that later. We express the risk reduction as a safety integrity level. ISA 84 uses standards or the levels 1, 2, and 3. And level 1 can give you a risk reduction between 10 and 100 times. Level 2 between 100 and 1,000 times. And level 3 will give you a risk reduction between 1,000 and 10,000 times. Still, level 4 is basically not used in the standards. If you find that you need a risk reduction in SIL level 4, then the standard says that you have to redesign your process or find other measures to reduce that particular risk. Okay, the overview. Here's that safety life cycle diagram again, and in the beginning we have a hazard and risk assessment. I assume that most of the audience will know and has even done those assessments already. What the standard will give you is some examples of which methods can be used. So we have the ALARP, or as low as reasonable practical. We can go semi-quantitative, so it's kind of like, okay, this is going to happen, and we just put a number to it, so we know certainly what grade of the severity of the calamity would be. There's a safety layer matrix method. There's risk graphs, either calibrated or not calibrated, and we have a layer of protection analysis. All these methods are just mentioned as an example of how to do the hazard and the HAZOP and the risk assessment. So a team that would do this kind of assessment consists mainly of process designers, instruments, safety, electrical, mechanical engineers, operators, maintenance engineers, and if necessary, a facilitator. But if you look well, then you see that all these functions that do the HAZOP are from the process plant itself. These are the people that are actually have the experience, the knowledge, and the day-to-day use of a process, and they know what can go wrong and where the hazards are in a process. You will not see a safety system vendor here. The safety system is not even in question here. We're just looking at what functions are required to achieve the safety. The facilitator, of course, is somebody who has much knowledge of the standards and very much experience in how to use it. And this facilitator can help you to do this HAZOP. We saw a LOPA analysis, layers of protection. Well, this is the form that the IEC standard gives as an example, where you, in the center you have the process, and layer for layer you can apply safety to that process from your control system, the operator himself, but also from mechanical protections or indeed safety instrumented systems. And the alarms are also taken into account. Outside that, we have mitigation systems. So if anything happens, you could have other systems that, for instance, contain a spill, or also fire and gas systems that will help extinguish a fire. And of course, plant emergency response teams, and then of course the community emergency response teams are also taking part in this. So the next step is we're going to allocate the safety function. So in the heads up, what we do is we find all hazardous events that are possible, and then we're going to say, well, this is a frequency that this could happen, and this is the consequence. And we're going to give numbers to that, and that will result in a process risk. And this process risk needs to be reduced. And so we have several means to reduce that risk, like external means, containment vessels, but also other mechanical devices, a ruptured disc, dams, dikes that could contain spills. And the last is the safety system. So whatever risk reduction cannot be met through external and mechanical means, the safety system will reduce that further until we meet a tolerable risk target. So the safety functions have been defined as what is the risk reduction here. The next step, in the same allocation of safety functions, what you do there is first you're going to look at, do we need an instrumented function? An instrumented function is a function that makes use of transmitters and valves and a logic solver. If we say yes, then is it a safety function? If we say yes, then we're going to see what kind of mode it is. Usually we go to the demand mode, where maybe once a year this event could happen. And then we have a safety instrumented protection function. And then we can choose, is it now a prevention or is it a mitigation? So is it an ESD, emergency shutdown function, or is it a fire and gas system? After this, we are going to document the safety requirements in the specifications. So we're going to describe what is the function of this particular safety instrumented function I have. So for each safety instrumented function, we're going to write down what it needs to do. And we're going to say what SIL level, what reduction factor it should have. And we're going to assign the I/O to the safety functions. Then we're going to say, is this now a valve open or closed, or is it a de-energized to trip, or is it an energized to trip? We're going to set the trip points for certain things that need to happen. Also the pre-alarms we need to have here of all the process, and also the process outputs and actions. So what needs to happen in the process. Then the functional relationships between the SIFs, between the transmitters and the valves, the failure modes, what can go wrong in this particular SIF. And of course we have our shutdown philosophy, we have our maintenance override philosophy. Also, we need to take in account that a safety system needs some time to react, and that's probably not only the safety system, but also a transmitter has a delay, and most certainly a valve can have a delay. So we need to know what is the required response time, and can we meet that with all the equipment we are using. And then there are several operator interface modes. The system or the process can be in startup, or it's in steady operation, or it is already shut down. The SIF may have to react differently in each situation. And then we need to find some abnormal conditions that are foreseeable and cater for that. And then what are the functionalities, especially for starting up and shutting down. The safety requirement specification is not necessarily one document. Mostly it isn't. It will have the basic functionality as mentioned in the previous slide, but it mostly refers to documents that already exist. The cause and effects diagrams, the I/O lists, the narratives, philosophy, shutdown hierarchy, the maintenance override philosophy. All those documents can be just referred to in the SRS to make a complete SRS. After the SRS, we can finally work on the safety system design. On here we're going to take into account what is the required availability. Note that availability is not really a part of ISA 84. ISA 84 is about safety. And safety is make sure that the system works when it's supposed to work. And availability is, of course, make sure that the system works not when it's not supposed to work. Very important, because this is what is about unwanted shutdowns. Then we're going to put together the system architecture for the safety system, the architecture for the sensors and the final elements. I will show that a little bit later. And then also we're going to take into account what are the failure modes of this system, and we're going to make the calculations. These are called PFD calculations, a probability of a failure on demand. And these calculations will show that the safety instrumented function meets the required SIL level or the required risk reduction. Then we're going to lay down the design principles, and the design principles make sure that your safety system is consistent, that for the same SIF you use the same architecture, for the same philosophy. You don't get a wild pattern of all kinds of designer independent choices that will compile your safety system. If you have a design principle, a document, then you will have a consistent programming, which is way better for future modifications. And of course that is very important here, because we're talking about a safety system. A confused engineer makes many mistakes. So, and we're going to document some more, like proof testing, what proof test interval is required for each SIF to make sure that it stays in the SIL risk reduction class. There can be said a lot about proof testing, but for this presentation that would go too far. Common cause failures. That is also one thing that safety systems is very important. A common cause, for instance, could be radio interference. Radio interference would interfere with how an I/O module would react or respond. If you have two of the same modules, they will respond identically. So that's a common cause. An earthquake, for instance, is a common cause. A flooding is a common cause. All these matters need to be taken into account. And of course, common cause can also be inherent to the system itself. The system uses the same cabinet. The system uses maybe the same backplane, etc., etc. And we're going to document how we do our calculations. That is what we do in the SIS design. So I already mentioned we are also going to define the architecture. And with architecture, I mean the following. Suppose we have in this green circle here, here's a safety instrumented function, and that exists of a measurement in the field and a valve to close something when necessary. Then if this SIF, for instance, has a risk reduction factor of 1, a SIL 1, then we might be able to only use one sensor and one final element. But you see, if you have higher SIL levels, it may be necessary to use 2 or maybe 3 sensors that you vote, and maybe 2 valves in series in order to achieve the higher SIL levels, for instance SIL 3. That is what you do during the SIS design. Then the application software. The ISA 84 gives this a lot of attention. There are many clauses to comply with, and it has its own life cycles. For different things, there are different life cycles. Well, to avoid to make it all too complex, if you use a certified system and programming tools, IEC 61508 exactly is the standard for the design of safety systems, hardware and software. So the products you buy, then you can combine the hardware and the software life cycle. And if you describe this good in your project documentation, you should be okay with that. The next step after the safety system is built, we are going to install it in the plant, and we'll commission it, and then we validate it. Installation and commission, most of us have been through that process. It's a very busy time, so you need to plan this very well. But more important for ISA 84 is that you have to document all activities. If you make little changes, if there is some problems, you have to document that. And because you're going to resolve issues which will change the system, most probably. And now that needs to be documented very well. Why did you do this? What is the impact on the safety requirement specification? It could be even in the HAZOP. You need to go back to the HAZOP in order to allow for that change. Validating the system, this is similar to the site acceptance test. You're going to follow the safety validation plan. The safety validation plan you write from the beginning till at this point where you say, this is how I am going to test the system. I'm going to test that all safety functions work as in the requirements of the SRS. Also therefore you need to plan well and from the start. After the system has been validated and before you really can start the operation, you do a functional assessment. And this assessment is the final check of the system if everything has been met according to the standards. So, very simple, a hazard and risk analysis. Has that been carried out? So are the recommendations from this analysis implemented or resolved? You need to all have documented that so you can check it in the functional assessment. Are design change procedures in place and properly used? You're going to check that. So even the procedural matters you're going to check during the functional assessment. You're going to check if the SIS is designed properly according to the SRS. More procedure checks. The validation will be has a final check, and all other requirements of the ISA 84 will be checked here. Then we go into the operation, maintenance, and repair, the operational phase. So during this phase, most importantly, you need to collect the data on any failures you might find in the system. So from transmitter to valve, including the safety system logic solver itself. You need to document the test results of anything you test while proof testing, for instance. If you have an actual demand for safety, you need to document that very well. That is very important information. And also, if you can actually claim that you have tested the loop if you have an actual demand. So that is a little bit lucky there. And if you have accidents, of course, you need to document a lot more, but also what actually happened in the logic solver. So this data you're going to use to verify the assumptions you made during the HAZOP and the SIL calculations failure rate. So the HAZOP, you're going to assume that something will not happen more than once a year or once every 2 years. Is that true still after you have a failure or actual demands or an accident even? Are the failure rates I use in my SIL calculations, are those still correct? Do the failures I find in the field match what I use for my calculations? If not, you have to go back and redo your SIL calculations, and you might find that some of the SIFs you have are not up to par with the safety and the SIL level that they are designed for. And then, of course, you do proof testing. You're going to test the transmitters, the valves, the logic solvers. Each one would have a different proof test interval. Logic solvers test interval maybe 5 to 10 years. The valves have the shortest test interval. Those are the most mechanical, have the shortest lifetime. And the transmitters are somewhere in between, but all needs to be tested. And then during the lifespan, of course, you have modifications, and sometimes you have a retrofit or what we call decommissioning. Doesn't mean that you take out the whole system and a whole bunch of safety functions. It's more like, okay, we have changed a certain process, so certain safety functions are not necessary anymore, so you're going to take them out. Well, for this, ISA 84 prescribes that you must have a management of change procedure. Here I show an example. There's some example reasons. Why would I have a modification or a retrofit? Well, I might find indeed that my safety performance is below the target. During the lifespan of the system, you find your failures and there's something wrong there. You might find some systematic faults, that somebody just made an error, or there has been an incident or an accident, maybe even in another plant, but that experience will lead you to change the safety function. Operators may request that the safety system works differently. There may be new legislation, but for instance, if you have to modify your control system, quite often you will end up having to change the safety system as well. So in any case, if you have a modification request, you are going to do an impact analysis study. Sometimes you need to go back to the HAZOP to see what the impact is. Most of the times you just try and find any hazardous changes. And if none, then you can more easily do, but mostly you will report that, and somebody has to authorize that report, and then you know how to implement that change. Whether you have to go back all the way to the HAZOP, or whether you have to go back to the safety requirement specification or just the system design. In any case, you have to follow this life cycle model again at a certain point where it's appropriate. So if you have a modification request, this is the checklist, what you do. You're going to check if there's HAZOP consequences, risk assessment, do the cause and effects diagram need to be changed? Is there the SIL target, could that affect the safety instrumented function you are modifying, or others as well? What are the changes to the safety requirement specifications? And again, you go through all the documentation, of course the application logic, the philosophies, the shutdown hierarchies, any test procedures that need to be changed, the operating procedures, the maintenance procedures. Complete, well, this is not a complete checklist, but it's a long list where you're going to check what is changing because of my modification. So, this is what the standard is all about. I must say the standard, of course, knowing the complete standard will take a long time, because training, I'd say about 2 weeks, and you learn a lot, but you have no experience at all. So you might just you need that experience, and that will come over the years. If you actually go work according to the standards, you will get that experience, and yeah, you might even become an expert in using it. So what does it require to comply? Compliance to the standard must be full. That is the most important thing. You cannot just comply. Yeah, you can comply to part of the standard, but then you're not compliant. There's no in between. And now that is the actual cost of a compliant safety system. The one-time expense, of course, the hardware and the software and getting this all in place. But on top of that, you have the life cycle expense. That's just a returning expense that you pay money for. So, wow, that's going to cost a whole lot more than a $5,000 CPU and a couple I/O. Yes, correct. But ask yourself the question: what is the cost of a shutdown? What of an accident or a calamity? And then ask yourself the question: so what is the prevention of each worth? Well, a calamity, of course, a lot of dollars, and an accident probably also, but a shutdown also costs you money. So we're looking here at a good safety system that is also very reliable or available. I see I have a question about availability. At the end, I will talk a little bit more about that. So the real cost reduction is getting the compliance, the full compliance, but in with the right approach. Don't step into pitfalls. Learn how to what the best practice is from the get-go. So, what should you do? Well, in the first place, you need to get individuals that are competent, trained, and certified. They need to know what they are doing. You need to assign one or more persons to your functional safety management. You need to implement that. Depending on how big your plant is, one could do the job, maybe two or more, but it's not a complete department, so to say. Um, Before you start, you have to have a coherent strategy from the beginning stages of the project. You need to include all the steps of the life cycle in that, so you know from the start what you need to do and when it needs to be done. And to help you through the phase of getting that safety system in place, then you need to look for industry expertise and project execution experience. That is very important. Oh, I think, yeah. Other things, considerations are that if you replacing your safety system, it can mean that you need to replace your transmitters and sometimes valves as well. How good are they? How good are they in the field? Do they have reliability data associated with them that they can be used in a safety system? If you can, use certified sensors and valves. Also, the S84, the ISA 84 has high standards of maintenance. So often this is overlooked, but the standard will mandate that you be very careful with that. Currently, we have new technology that offers predictive maintenance, and especially safety systems require this. Control systems mainly can work through a whole lot of little issues. Safety systems can't. Little issues will become big. So we have asset management systems. And these asset management systems are not only require, or these asset management systems not only help you to maintain your safety, but you can also prevent unwanted shutdowns. The management systems can do preventive maintenance or preventive diagnostics. And you should make use of these capabilities. If you do, again, your cost will go down. So what I got a couple of do's and some don'ts here. Supplier selection. The supplier of your safety system, you need to have some selection criteria for. You need to look for long-term support there. If you are considering replacing a safety system right now, it might be because your safety system is not supported anymore. That's very well possible. Look at the vendor's track record. You want that long-term support. So what is the track record of this vendor? What kind of technologies are in the roadmap? Is this vendor basically on a standstill in development, or are they continuously making newer and better stuff? A Mac approach. You might consider to have this vendor take a whole lot of work out of your hands by let the vendor do the transmitters, the valves, and all the automation for your new safety system. So you can keep focusing on the other parts of the standard that you need to comply with. Make sure your hardware and software is IEC 61508 compliant. I already mentioned this. IEC 61508 is the standard that is the basis for the ISA 84, and the ISA 84 requires or points to the IEC 61508. 61508 again is the standard that is for the safety system, hardware and software you're using. If both hardware and software are compliant, you can avoid very much work you would otherwise have to do. Make sure that system also has a high availability. One shutdown prevented can already be the worth of the safety system itself. And of course, last but not least, you need to integrate security with safety. What you should not do. Maybe you have this in mind. Can I phase my new safety system? This is not recommendable. You will have to redo many activities. All the verifications, validations, you have to redo with each and every edition. It's way better to do it in one go and have all those activities done only once. Can my plan be online during a replacement? Well, I'd prepare for being offline. If you need to replace transmitters, valves, cabling, it's probably going to end up that the plan be offline. Just prepare for it. So that was the standard and what you should do to avoid paying high costs for a safety system. Here I want to show what Yokogawa can do for you if you are looking to select a vendor. Yokogawa is a company founded in 1950. It's a global company with a total assets of about $4.4 billion US. Here's the other figures. We have about 20,000 employees worldwide. In America, North America, we have the following locations: in Newnan, in Sugar Land, then in Calgary, and in Mexico City. Our global market share for ProSafe RS in refining, you'll see that is the fat blue line. We became number one in 2013. ProSafe RS is installed all over the world. Currently, we almost have 9,000 controllers in the field, and these controllers serve about 1.5 million hardwired field I/O, and that is since 2005. The other thing Yokogawa offers is what we call progressive compatibility. If you look at ProSafe RS, was in 2005 released, and then it was on our network called VNet. Currently, ProSafe RS is on our VNet IP, but look what we did. We have a little gadget here that will make sure that these systems can still talk to each other. So in the progression of the system, we still be compatible with the older systems. And we have done that with our DCS since 1975. And we're not planning to stop that policy. On the other thing is that if there is an order termination during the lifespan of a product, then we will announce that 1 year before it will go into effect. Anything will be normal during this 1 year. Then in the first 5 years we're in phase 1, you can still buy parts, spare parts, etc. And then phase two, we have another 5 years where we have special ways to for you to obtain spare parts, and then the end of support is then you cannot buy any spare parts anymore, but then we're 10 years later. And in the meantime, we of course have developed new stuff that will replace what is terminated in this diagram. We have a service and support the spare parts and the lead time. We have consignment programs for spare parts to deliver within 24 hours. Well, typical availability is 8 weeks, but the consignment program really is a speedy delivery. Our service organization has dedicated safety engineers, so they can answer your questions. And there's also options available that you get on-site long-term support. People actually on-site to work on your safety system. Worldwide, we have 240 functional safety engineers and experts worldwide. We have a call center. You make one call and you can reach a safety expert 24 hours a day, year-round. Then for ProSafe RS, I'll give you some highlights. It is used in ESD, fire and gas, BMS. If you want to connect it to your process control system, you can have a dual redundant communication. It's just 2 modules, and you can either do it TCP/IP, RS-485, or RS-232 with Modbus. ProSafe RS can be used in a single or in a redundant mode. It's flexible. You could have dual inputs here and a single CPU, or a dual CPU here, single inputs, single outputs, or everything dual redundant. One of the differences between other safety systems and ProSafe is that in a single module configuration, you can use it in SIL 3. So if this input should fail, of course you would have no shutdown, but you will remain SIL 3. You have no degradation of the safety. And also, of course, this will increase your availability, i.e. unwanted shutdowns, enormously. Security, connection to the safety system for engineering purpose goes through a special NIC card. It's a Yokogawa-made card. It has the encryption, random changing keys, the bandwidth partitioning. It's a 1 gigabit PC card. We have the Achilles program. 30 million plus tests are performed, and then if you pass those tests, you'll be certified. So is ProSafe RS. We have remote I/O. We can go up to distances from up to 31 miles in a star configuration. Our I/O modules are connected to field termination boards with signal cables, or another way I will show you that, like these field termination boards that connect the I/O modules. Probably interesting for many people who are really looking at changing out a safety system. This is what we can do for you. These are actually actual systems. The cabinets have not been finished. This is just the under construction wiring. But here's the I/O modules. They are connected with system wire to the field termination assemblies, which will connect to the field wiring. That is one way to do it. This is a standard cabinet, Hoffman or Riedel, which can be used in equipment rooms. But here is a very special cabinet, which is going to be outside. The termination here, by the way, is done directly on the I/O module, so you can reach a very small footprint. This cabinet, again, this is a stainless steel cabinet. It stands on a pedestal for flooding and water. It is pressurized. It has all the equipment to control the pressurization inside. It's airtight, and this can be used outside. It is this one actually goes to a platform where the only thing that will cover it is probably the deck above it. And you see the I/O is terminated on these terminal strips here. So that's what we can offer you there. Very flexible. I/O module range. Have a quick look at it. We have thermocouples. We have a wide range of uh, outputs, and we have an analog out as well, analog in as well. So just look at it. This presentation will go. You will get a link to it, so you can have another look. So this is about it. ISA 84, how to comply. Yokogawa Pro Safe RS. I think we could be a very good candidate to help you and support you doing the achieving the ISA 84 compliance. So now let's have a look at some questions. Now I can turn my head finally to the big screen where I can see. Okay, I have a question from who asked the question? Oh. Okay, yeah. Somebody asked, what about reliability? Could you elaborate a little bit on that question, maybe? It may have come in a point way earlier in the presentation. Okay, I'm getting some help here. Yeah, reliability. Okay, availability, reliability, safety. The standards, well, we use mostly the term safety and availability. Safety is of course how safe is my system, and availability is how available is my system, in a sense. Will it not break when it's not supposed to break? Will it not cause a shutdown when it's not supposed to cause a shutdown? That is availability. Reliability, yeah, those two together, of course, that's the reliability, but I usually stick to the terms safety and availability. I hope that answers your question. You can type a new question if you want to. I'm just going to the next question. Can you provide a bit more explanation about availability? Yeah, availability is a number that will, usually it is set in percentage, telling you how available a system is. So some system, usually it goes from, it is in the range of 99.99% available. That means that it is 0.1% unavailable. What is that? It is not such a good measurement idea. 0.01% non-available basically means that it is 1/10,000th time of the time not available. Yeah, I don't know if that is so. What you usually say is, what is the average time between failures, the MTBF, and that goes in years. That says way more about the system than the percentage. So if you have a system that has an MTBF of 20 years, that is a pretty good system. That means that in the 20 years you can expect it to fail once. I hope this answers your question. You can ask more. I will go to the next questions. Is there a major difference between 1996 and 2004 editions? Will a system designed as per 1996 be compliant with 2004? That is a good question. There are certain aspects that are different. I cannot go too deep in that right now, given the time and the amount of questions. Please send me an email and I'll give you some documentation on that. You will see my email in one of the later slides. Thank you for the very good question. How much do HAZOPs cost for a small-scale plant? Yeah, well, in dollars, of course, that is very difficult to say. But as you've seen, you need to get the right persons together. You need to have enough knowledge and enough, let's say, creativity for everybody that they can find hazards in the plant. And then, yeah, you need to go sit together, a small-scale plant, maybe a couple of weeks before you have final documentation. Some HAZOPs can take a year if it's a really large installation, and probably use more people as well. So, yeah. From weeks to a year, I'd say. Phase 1 still buy spare parts. Phase 2 special ways to get spare parts. What is as special ways? Yeah, there we go into a phase. Let me think where you can pre-order them or have them pre-stocked, or we might end up to getting a used spare part, a used but completely done unit. Uh, Can you please comment a little more on IT security risk as it relates to the actual syslogic solver? How is this risk mitigated in Yokogawa systems? Is this risk mitigation addressed in current industry standards? Soon in current industry standards, we do Yokogawa as a whole in our user interface equipment. We use the current security settings, the protocols, the protection. Um, so and the access and authority. So the user ID, password implementations that are common in the Windows atmosphere. So that is what we do for that. Let me see, what time is it? We are almost running out of time. I'm going just to the next one. Can we support clients in preparing SRS for the project? Yes, we can. Most definitely. We have a lot of knowledge in that phase of the project. Of course, it is not very much related to the actual product, ProSafe RS, but we can support you. We may help you getting a good template together, but also do the calculations, do the architectures, and find the databases with the instruments and the valves. Yes, we definitely can help you preparing the SRS. Bela Liptak, do we continually rely on operators to make the correct decision under extreme situations? Safety statistics tell us that the number one cause of all accidents is humans. Yeah, no, we cannot actually. An operator is pure mathematically seen. An operator is situated in the category where you have a failure on demand, of 1 out of 10 goes wrong. If you look in the SIL table, that number is not in there, so an operator is actually rated SIL 0 because he has a failure rate on demand of 1 out of 10. So no, we cannot rely on operators for safety at all. So that makes this question not very necessary. It's just don't rely. So, and indeed, the cause of all industrial accidents is human. Yeah, you got to be careful with that. The cause of all industrial accidents is a row of events, so to say, and that is the most usual cause. A whole bunch of things happened at the same time, or just after one another, and one thing leads to another, and there's the accident. Okay. Human error. One could refer to 3 Mile Island, where the operators poured water into the instrument air supply. Correct. That is pure human error. Do we need a shift in the operator interaction as part of instrument protective layers, independent protective layers? Do we need a shift in the operator interaction as part? I do not really understand that question. Could you please elaborate? I go on because we're running out of time quite rapidly. Should fire gas be part of the SIS and initiate a shutdown? Yes. If you want to use your fire gas as a mitigation system, it should be able to automate a shutdown. It should be able to automate fire pumps, the actual deluge, etc., etc. Yeah, executive action for a firing gas system. Okay, well, it is time. It is 12 o'clock. If you have any more questions, my email address will appear very soon, and I will have to end the presentation, the webinar, right now. Please send me an email. I'd be very happy to answer them. Thank you very much for your attention.